Welcome everyone to Carney Conversations. This is an opportunity to hear from leading experts and their opinions on topics of major current interest in brain science. I am Diane Lipscombe, the director of the Carney Institute for Brain Science and professor of neuroscience. I'm joined by my colleague, Chris Moore, who's the associate director of the Carney Institute and also professor of neuroscience. And we're here with today's expert, Professor Stefanie Tellex, to talk about humans and robots. Stefanie Tellex is an associate professor of computer science at Brown, and she's done some very important and beautiful work in the area of robotics. She constructs robots that use natural language to communicate with humans. And Stefanie predicts that by 2040, every home will have a personal robot which can perform those tasks that we all hate to do the laundry and clear the table, all kinds of things like that. And so we will see. We're going to hear a little bit more about what that will take for that to happen. And Stefanie Tellex is also a passionate communicator and a teacher. In addition to her phenomenal teaching at Brown, she's also been involved in outreach activities to high school students to motivate and bring along the next generation of robotic scientists. So before we start to ask Stefanie some questions, Chris and I'm just going to mention that we really look for audience participation. And so you can, at any point, go ahead and use the Q&A function at the bottom of your screen to type in some questions, and then Chris and I will get to those as soon as we can. So Stefanie, thanks for being with us. It's a real thrill.
Thanks for having me.
You're welcome. So I get the privilege of asking some really simple questions to get this going. And so I was hoping to just start off, can you define what a robot is? And you know, when does a machine transition from being a machine to becoming a robot?
Yeah, so there's actually not consensus about this in the field of robotics. But for me, a robot is bringing three things together. It's bringing a sensor, so something that lets the system know about what's going on in the external world. So that could be a camera. It could be a laser rangefinder that measures how far away something is. It could be a thermometer or a pressure sensor. A drone might use a pressure sensor to measure a barometric pressure to measure how high it is. As you go higher, there's less air pressure. So a sensor, and then an actuator. So something that makes changes to the world. So that is often a motor, something that can move the robot. It might be a wheel on the ground. It might be a motor in a joint of a robot arm, moving an arm around. It might be a motor in a drone. So here's my drone. And it might be spinning the propellers to make the robot go up or down or something else. And then the last piece is compute. So some kind of computer that is performing computations using the sensor input in order to make decisions about what the actuators should do. Now that definition says that something like an air conditioner is a robot because you have a temperature sensor and you have the fan that's driving the air through the unit, which is a little weird, but I kind of like it because it's sort of these three things that you bring together, that you have a computer that's measuring something in the world and it's making changes in the physical world.
Or our cars. I mean, like.
Well, yeah, I think the cars are a little, a little easier. It's a little easier to accept that they're robots. In this world where Waymo is doing, unmanned testing in Arizona, it really is. There's no human. It's driving by itself using sensors and actuators. But absolutely, a car that's doing cruise control. It's measuring the velocity of the car, and then it's actuating the gas pedal to try to keep you at the target velocity.
So in that, in that definition, and thinking about where, your, where your research becomes really kind of critical. I was actually listening just recently to give a shout out to Harrison Ritz, who's a graduate student in Amitai Shenaf's lab in the Clips department. And I knew that we were going to be chatting with you, and I was listening to his presentation. He was talking about how humans make choices, and just kind of applying engineering control theory.
Yeah.
And then as I was thinking about, we're going to be talking to Stefanie Tellex about, the robots and making choices for humans. And so, and of course he was talking, I should continue my thought that thinking at the simplistic level, cost benefit. So what's the cost of doing something, and then what's the benefit of a particular action? So, are you? I mean, how does your field think about this in terms of placing value? So on a particular choice, in terms of building a robot that is going to be making decisions that we expect would be human-like. And so what's the value system that you think about there?
In one sense, I mean, we use the word value in a different way, in a technical way, where we just say there's like states, the way the world could be, and then we assign numbers to those states. And we call that the value of being in that state. And the higher numbers are good and lower numbers are bad. And then we kind of say, okay, somebody else's job is to assign those numbers, and our job is, given those numbers, to try to make decisions so that we maximize our value or maximize our reward over time. But then, the question is, how do you get these numbers, and where do they come from? And there's not really a consensus answer. I mean, a lot of times it depends on the problem that somebody's working on. So if, for example, you're trying to make the robot open a door, then it's very natural to assign high value to having the door be open, and hope that that can enable the robot to figure out what to actually do to cause the door to be open. And if you may have seen a number of years ago now, Google Brain did this project where a robot actually learned to open doors. And one very interesting thing about that project is they actually wired the doors. So they put sensors in the doors, to actually detect unambiguously whether the door was open or not. And that reward signal, that value signal, was what the robot used in order to learn if it had been successful or not successful. I think in my own work a lot about robot language, making robots understand language. And the way that we think about that in my group is trying to go from words in a human language like English to some representation of those numbers of what states are good and what states are bad based on what the person was telling me to do. So if they tell me something like, go down the hall and wait near the door, what I want is to write a program that will cause the robot to have high value for being down the hall at the door, and then ultimately to drive its actuators to drive down the hall and end up at the door. Of course, you could tell the robot to do something bad, but I don't think that much about that, partly because it's so hard to get the robot to do anything at all, that I just sort of say, well, I just want it to do what the person said to do, and I trust the person. It's the person's job to impose moral orders. Another professor here at Brown, Bertram Malle, in CLPS, does think a lot about values and norms, and when and how to enable the robot to detect an order that might violate a norm or violate a guideline that it's been given otherwise, so that it can try to respect some value system that's been imposed on it.
Right, but if we focus on what you're doing, you're still at that ground level of very, very simple kind of binary tasks. Go do this.
We think, what we're trying to do is expand.
I mean, I don't mean to say your research is simple. I didn't mean
No, I
to
know.
suggest that. But go ahead.
What we're trying to do is expand the scope of the things the robot can understand. So I like to say people want to talk to a robot about anything the robot can see and anything the robot can do, anything.
Right.
So that means we need models that can understand anything the robot can see and anything the robot can do.
Right.
And a lot of my group's research is focused on expanding, to anything, trying to say, well, look, this category of commands we couldn't understand, and here's some technological, some mathematical apparatus that lets it understand, and let's go build it out and see how well it works.
Right. We're going to get into a little bit more of the nuances around this, I think, a bit later, in terms of, should robots have rights? Like, how close will they become to being human-like and making human decisions? But of course, each individual human, depending on context, is going to weigh, cost benefit in different ways, and of course that also differs across different human beings. But like, maybe I think we're going to come back to that. There's a number of questions about this, but before that, so thank you. Like, I think it's really good to get like this ground, this framework in place. So I'm going to now move over to Chris. Chris, I know that you've got a couple of questions that you want to kick off and with to get discussions going with Stefanie, and I'm going to start to look at the questions that are coming in from the audience.
Great, thanks. I think the Zoom was exerting its robotic control over my access to information. It just kicked me out, so I apologize.
Welcome.
If the community of robotic Zoom control has been censoring me. If I missed anything I should have caught. It's so cool to get to talk to you. It's just, this is a really, really, really relevant part of like the bigger thing that goes into understanding minds, is what if you could create them. And and it's such a fantastic problem, like not thinking about it a lot, but now getting to rethink about it because we're talking to you. It goes all the way from embodied engineering all the way over to language processing. One of the projects I noticed that seemed like this really interestingly bottom-up but engineering side. We think about a lot of deep learning as maybe coming from bottom-up approaches. The Million Objects Challenge I was reading about on your website. Is that like deep engineering? Like in the learning sense, it sounds like a really cool, I guess, objective data set.
That was started in response to like this mismatch where, deep learning is really happy when it has lots and lots and lots of data. But a lot of the data that's accessible to deep learning systems today is text-based data or image-based data, but it's really different from the data that a robot is given to a robot. And it's also really different from the data that a human or an animal has as it's moving around in the world. And so what we were trying to do is figure out a way to collect a really large data set of experiences of manipulating the different objects. The project kind of failed. Like, we really failed to scale up to the robots that, the number of robots that we wanted to capture. In part because I felt that we were missing a theoretical grounding of what it meant to be a robot and what it meant to computationally, think about having perception and action and communication all happening in the same system. And I didn't want to collect the wrong data. I don't want to do a lot of work to collect data and have it be the wrong data. So we kind of pivoted, after we collected a bunch of data, and we were like, now what? And we realized we were really missing this decision-making framework that we've since put a lot of energy into trying to figure out. And I think, I actually feel that we're now nearing a point where we can pivot back to saying, okay, now we think we understand the decision-making framework. Now we can scale up to collecting a lot more data and trying to leverage that data to make robots that do useful things in complicated environments.
Yeah, that's awesome. I mean, I literally one of the, well, Sapiens is one of the books supporting the tower on which my computer sits right now. And there's a pocket history of human evolution next to it. I mean, that does seem like the big challenge, right? The blunt force of evolution embodies things, right? And not perfectly and without the goals, and yet robots have this wonderful goal directedness to them, but they also need that like experiential, just got to make mistakes and end up crashing in the world, right?
Yeah,
Quality.
yeah, make mistakes and crash, but also learn from those mistakes.
Yes,
And
exactly.
it's a different kind of learning than is done when you're trying to do machine translation, for example, from, you know, lots and lots of text-based data sets. Because you're dealing with like multimodal data, you're dealing with images, you know, I mean, we think about camera images, but you're dealing with data coming from your sensors. But then more than that, you get to move your sensor.
Yes.
You know, you get to, you get to foveate and saccade your eye around. You get to turn your head and look.
Yep.
You get to pick something up and hold it really close and, you know, examine it.
Yeah.
And that decision making is essential, I think, in how we see the world. You know, it's sort of well known that you even see the blind spot in your eye, right? Because you're just saccading around and you get this sense that you have the whole world, but really you're foveating on this one little tiny thing. So fundamental to how we see the world is this idea of active perception. I'm looking at what I care about. I'm gathering information all the time. And that's something we've been thinking a lot about in our robot work, to try, how can we computationally do that? How can we integrate perception and action so that we're able to gather information actively, and learn to do that, you know, over multiple different sensors and over a long period of time.
Right, and it seems like one of the real tensions is it's really hard to keep that in simulation space, right? Like you really need the robot to go exist in the environment and try to do the thing again and again, and then, you know, meet with the scorn of its master, and
I mean,
have that be a value symbol. And yeah.
Yeah, there's something about the real robot. You know, we keep coming back to, we have to build the real robot. We have to make that video or do that user study with the real physical robot. Because it's so easy to slip to the wrong problem or to an easier problem. You know, we will often go back to simulation. Like what you know, my group kind of bounces back and forth between the real robot. We'll figure out what the one problem, not the problem, but, you know, one of the problems, and then we'll make a simulated model of that problem. You know, trying to capture just that one problem and nothing else, and solve it in simulation. But then we always go back to the robot, you know, and say, okay, here's what we made, and let's try it on the real robot and see, you know, see how well it works. And we're held back right now, to be honest, by simulators. You know, our deep learning algorithms are so data hungry. It would be really nice if we could simulate data, and not have to run our real robot, you know, for 100,000. Some of these algorithms want 100,000 hours of data. And we're finding that, you know, simulators can give you really good photorealistic images, but then their physics sucks. You know, they don't model very well what happens when you drop something and the ball rolls around or something. Or they give you really good physics and they can, you know, you can drop a ball and roll a bowling ball and the pin's knocked down and all the physics is good, but it looks like a game. It looks animated and you can't use your physics, you know, your photorealism. Or you can get both of those things, but it's really, 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 really slow. Like slower than real time, and then you're like, well, that's not helping either, because I want to run it, you know, I want to run it for hours and hours and hours.
So Stefanie, just kind of as a connected question coming in from the audience, there's a couple of questions kind of connected around, like, what you mentioned images, but what could you define a little bit in more detail what data you are in fact collecting?
Yeah, there's sort of standard sensors most robots will use. So the camera, an RGB camera that's giving you 30, 60, or 100 hertz. That's, you know, 30, 60, or 100 times a second an image. You know, so just like the image of me you see on your screen. So it's usually a square. Although there's, you know, there's a lot of research in different cameras. We just bought a stereo 360 camera. So it's two images, and each one is like fisheye, so it sees 360 degrees around the camera, and we're going to stick it on our robot and then use it to do VR. So you'll be able to see all this stuff in virtual reality. We often use depth cameras, so that's RGB plus depth. So at each pixel, you shoot a ray of light out and measure how long it takes to come back. That's one way. There's other ways, and from that, you know how far away that pixel was from the camera, so you can get information about the 3D structure of the world without having to do stereo, complicated, hard stuff. Then we use various kinds of joint encoders. So like if I have a robot arm that's moving, I'll have a sensor in each joint to tell me the angle. I'm using my arm as a robot arm, but like to tell me the angle of that joint. And those are typically very precise. Industrial robots, their job is to like know exactly where that arm is down to like 6 microns or something for the end effector, which means very precise at every single joint. So a joint encoder, or I might use a wheel encoder on a mobile robot. A wheel encoder will tell me, it basically counts how many times the wheel has spun. So I can measure both velocity of the wheel as it's spinning, and also I can integrate that to measure distance, approximately how far the wheel's gone as the motor, as it's driving around. And then we use, especially on drones, but on other robots too, we use IMUs, inertial measurement units. So that's the equivalent of the human's vestibular system. So the sensor that lets you, I have this exercise with kids where like you sit in a rolly chair and you close your eyes and somebody spins the chair and then you have to point which way, you know, the clock was or some landmark. And you could do it pretty well. And then they push the chair and they have to say, you know, which way did I move? And you can do that also because of these bones in your inner ear or something. So we have the same thing on our drone. It's a little tight. It's like insanely small. It's like this chip here on the drone. This little tiny micro electromechanical system, MEMS, a 3-axis gyro and a little mass on a spring measuring acceleration in the IMU. And that's especially for drones, very important to know. As I start to tilt a little bit, I can very quickly measure that tilt and correct it or not if I'm trying to tilt to move somewhere. So those, I guess, are the main sensors most people use. LiDAR and radar is really important for self-driving cars. So those are also electromagnetic kinds of sensors, shooting lasers or radar out at different frequencies to measure the distance between the sensor and stuff.
Mm-hmm. So a lot of what you're describing, you know, that there are very strong parallels to what the human brain can do, remarkably well. We're always, I don't know, I don't cease to be amazed at the integrative capacity, and then the weighing of different sensory inputs, and then somehow we can be able to give reasonable output most of the time. So, but and then for the kind of echolocation comes to mind as well, as you were talking about sending a laser out, and, the rebound and the timing.
And we use actually ultrasound also. So we do actual echolocation on one of our robots. When you're near it, you can hear it go tick, 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 because you can hear the sounds as it's projecting.
Cool. So how much of what you do is anything that you do, or anything that brain scientists have learned about how the visual system works, or how the stimulus system works, or how bats do echolocation? Does any of that help you in your research or not? It seems like a simple question, but I
mean, for me, at a high level, for sure, one of the biggest things I've taken away is how modular the brain is, and how, there's a language area, and there's a vision area, and there's the forebrain that's doing the decision making. Right. I'm sorry if I'm using the wrong words, but
no. It's
yeah. But that modularity is in some ways encouraging to me, because that's how we as engineers, we have to build things that way. And it makes me encouraged that maybe we can figure out, some of these pieces, because we see these same pieces in the brain. And you know, we're also really inspired by how people, like the sensors people have. You know, so we think about the vestibular system and the eyes, and what we do with the eye. You know, I've been thinking a lot about like what do you, you know, how you look and turn your head, and feel with your hand, and proprioception. I that's another one. The joint encoders are giving you proprioception. You know, it's hopeful to me that because people can do it with those sensors, that we can do it with those sensors. You know, we can use the same sorts of sensors. Although we also, you know, RGBD is cheating in some ways, right? Like the depth humans don't have. There's really cool like UV cameras and infrared camera, you know, that you can see stuff that humans can't see, and sense things, ultrasound and stuff. So it's okay to cheat. I don't mind, but it's also, you know, I think inspirational to see, you know, how people do it, what sensors they're using.
Yeah, that's actually that last part, the sentence about like what are you learning that we can't do, and there was a question about, you know, are there other kind of technical advances that have kind of changed the way in which you change your research that you could think of. I'm sure that happens all the time. We're always learning and adapting and incorporating advances from other areas and other disciplines. But so you gave you gave one example. Is there?
Yeah, I mean, you know, deep learning itself, I think you can look at as that.
Yeah.
You know, obviously inspired by, you know, neural architectures, are called neural architectures for that reason. You know, Josh Tannenbaum's work, I don't know if that counts, but like, I was really fortunate to take his graduate class when I was a PhD student at MIT. And the idea of Bayesian models and Bayesian modeling drives a lot of what we do. Even if it's not cool anymore because deep learning kind of came in, we still are driven a lot by it. And you know, I read Josh's papers, and I'm inspired by them. I actually admitted a PhD student who was previously a researcher in Josh's lab, and we're really excited about collaborating back, you know, with him through that student.
I mean, I agree with you that Josh is fabulous. That's a great, like the level of abstraction he manages to capture seems perfect for like that. So one thing that is sort of springing to mind when we're talking about the question of needing the robots to be embodied, like one of the arguments that is made in evolution is that the thing that just launched you know, the separation of human language from other kinds of animal communication was the intensely social behavior, right? It wasn't just watching so you can coordinate to have a pack of hyenas corner the wildebeest. It was knowing these really like detailed facts about that hyena has that relationship to that hyena, therefore they can work in a team, but these two better be independent. So when we approach the prey from that kind of, and there is a really good set of arguments. You can take them for what they're worth. That, you know, for example, the size of different monkey troops really nicely predicts the size of the forebrain. It's a kind of argument, right? So is there some way to create like a social robotic environment? I mean, there isn't simulation, but you just get a huge warehouse and let the robots learn from each other by having to get value by interaction. Like, or is this way too embodied in sci-fi?
There's people that do this. One example, a lot of it does happen in sim, but like there's some really beautiful work in using DEC POMDPs, decentralized partially observable Markov decision processes, showing that essentially that if you stick two agents in the same world and you give them the same goal, but they don't know each other's state and they're trying to figure things out, essentially that the optimal policy, the way that they solve that problem is by using language. Like a language is created by the agents so that they can communicate their state to each other so that they can solve the problem that they're working on together. So actually some of that work was done by Chris Potts at Stanford, who you may know, and he's more of a CLPS person. And I think Noah Goodman was also involved.
Okay.
Yeah. So that like, so that's definitely something that people think about. We think about it less. I definitely think that there's a large social component to language, but I also just think there's a lot we don't understand, even if you look at like, what dogs and horses can do, that we're still trying to get our heads around. And so that's
Sure.
kind of the level we're at. More than, I mean, I don't know, the language we understand is definitely more complicated than what a dog can understand, but the ability to sense, perceive, and act in the environment is nowhere near what a dog can do.
So is there a threshold or a marker that you're shooting for in terms of the natural language goal? Like, is there a moment where you're gonna be like, oh wow, we just turned a corner in that in your research?
I don't know. I mean, I'm very opportunistic about my research. So like, we really, the most important paper is always the next paper. And so, I have been inspired by making a Turing test, that is a computer that can talk to you as if it was a person, that's indistinguishable from a person. But I think we're a long ways from there. And I don't know, I think, I don't know if it's going to be like, like a sharp barrier, or we're just going to, we're going to get more and more functionality and more reliability. And at some point, we're going to say at some point in the last 5 years, we've crossed, we can't say exactly when, but we've passed the Turing test, we see, there's this old, I don't know how to say it, like this old rule or complaint in AI that like once we solve it, it's no longer AI. So like for a long time, solving chess was AI, and now we're like, no, that's not it. It's not good enough. Now we just did Go, but that's definitely not it. We could do Jeopardy. Jeopardy's got to be it, but not quite. We're not there yet. But I think it's important. But you can see that this is steady progress, and I think that at some point we're going to look back and say that we've crossed that line. And then I think I saw this as one of the written questions that I think robots will have moral rights at that point. I believe in strong AI, so that says that our brain is doing what it's doing through computation, through computation, and the Turing, the Church Turing thesis says that computation is universal. So in principle, I absolutely think that a computer with sensors and actuators can do everything the brain can do. And therefore, I think that means, by corollary, that such a computer that was doing enough things that the brain does, would then have moral rights. Are we there yet? I don't think so. And the other thing is that we can lobotomize, or not even lobotomize, we can just not give them, so like, if we can not put happiness and sadness in there, and or we, like it I do think that we will be able to build machines or grow machines or learn machines that have moral rights, but I also think that there'll be a spectrum, just as you look today at our spectrum of living things, like we think chickens have moral rights, but we stick them in factory farms too, and they certainly have less moral rights, I think, than people. There's consensus about that. Most people would say that, I know not everybody. And I think it'll be similar for our machines. There'll be a spectrum.
On that, continuing this theme a little bit, which I think is a lot of speculation.
Yes, it is.
Which none of us are particularly comfortable with, being scientists. But, so maybe you could imagine, that robots should have a certain set of rights. What about freedom of speech?
I don't know. I mean, it to me, it's like so far from where we are that the question is, I don't know.
Okay, fair enough.
I mean, would you say that a chimpanzee has freedom of speech? I have no idea. Like, has somebody thought about that? I don't know.
That's fair.
Can I ask a question about how far away we are? Which is when
Yeah.
Botvinnik from DeepMind recently came a couple of years ago, even to
Yeah.
talk at this great computational neuroscience meeting we had here. He pointed, his claim, so I'm quoting him, was that they're legitimately concerned about what's going to happen in the wild with some of the deep learning algorithms they're creating and frameworks they're creating. So it doesn't, in that sense, in the ability of those systems to independently
They made
operate
me
in the way they
mad.
could.
Those guys, like, so like this was when it was OpenAI that released GPT-2, and they didn't release the whole data set, and they were like, we're afraid that this is too powerful and we can't give it to the world. And it was two of my students right here at Brown that were like, no, this is not science. This is not what we do. And they, you know, they recreated it. They like, and my feeling about that was, it was I just felt I felt that they were that OpenAI was exaggerating the danger, mostly to get press coverage, and not really accurately assessing, you know, what the danger was, and also how much not releasing it would mitigate the danger, you know, because two undergrads at Brown were able to reproduce it. So, you know, sorry, but like, you know, you didn't actually take that many precautions. So, and I don't know, I definitely think that there's moral concerns with any new technology. I worry a lot about fake news and Twitter bots and, you know, the divisiveness that's happening in the world today. And I think a lot of that you can point back to, like, well, I have really good machine learning algorithms that learn what people click on, and the effect of that is making you click on really provocative but maybe even wrong things that, you know, grab you, and you have to read it, and then
Right.
you know, your brain is changed, and now, you know, we have this really divided country. And I worry about that a lot more than I worry about GPT-2 waking up and taking over the world or something. Right.
Yeah, the discovery by those bots that the sympathetic parasympathetic dysregulation is going to drive us to click, right? The rediscovery that people can have that kind of response. There are claims you can trace it to a surge in totalitarianism, even, you know, like that. There are at least claims like that you can actually map the way governments have gone as a result of how successful those bots were at getting people to click. And the clickbait was always something that enraged them or upset them or reached them at this visceral level, right?
Yep.
So you're right. You're right. We already had the problem is here in that sense. Can we say that there are therefore immoral bots, or they're just immoral makers of bots in that sense?
Yeah, I mean, I think it's immoral makers of bots. You know, it's or maybe not. Some of them, I'm sure, are immoral. Are doing things to try to get power over people, over other people, and I think I will say that's wrong. That's morally wrong. You shouldn't do that. But other people using these bots may not have thought it through, or may not realize the effect, you know, on people, and it's hard to realize it. You know, I mean, I don't think if you had asked Mark Zuckerberg when he was founding Facebook, you know, would people blame him because Trump got elected? I mean, that's a stretch, you know, like that's a pretty big leap there, right? Like,
you know, I think it is, I mean, to bring it back to perhaps make a more general point, I think we all know when we're in kind of this, in research, I mean, like we're doing something to discover something new, and then we have a particular motivation for doing that. The discovery itself has its, you know, has its own course, right? And I think that is true, you know, whether that's in robotics or whether it's in biology, that we really don't know as discoverers or creators what in fact, you know, will ultimately be how this discovery will be utilized. So, you know, I think that applies to all discoveries, and it could be a very short-term impact, or it could be a very long-term impact. I mean, we don't, like, you're building knowledge and you're building information, and people use that information by definition.
Yeah.
So, you know, I think this conversation is actually coming back to an earlier question, and perhaps somewhat more direct, which is, you know, are there practical, you know, rules or guidelines that your field uses and says, like, you know, someone referenced Asimov's laws of robotics, but, you know, is there, you know, are there these guidelines? Do you have community? You must have communities who get together, and, you know, you'll have discussions about what might be, and, you know, where would lines be drawn, and do we have some fundamental guidelines and rules? So
yeah, we really don't. I mean, we have the guidelines I can think of are, like, you know, research malfeasance, you know. They, you know, things like, you know, if you make a video of the robot doing something, you know, it has to be one take. You know, you can't take the first half and then fix some problems and then take the second half, you know what I mean? Or if you do, you have to say that you did that. You know, a lot of, you know, if you write that the robot did X in your paper, the robot had to have done X. You know, research malfeasance.
Right.
Don't do that.
Right.
You know, you should train on your training set and not report results on your training set. You should report results on your test set. That sort of thing. Of course, we have the IRB guidelines. So whenever we're doing a human subjects study, we have to go through the IRB process and show that it's safe before we bring people to our robot and have them interact with it. So those come from, you know, the human subjects rules, the Belmont Report and such.
Well, the R is there in that acronym. Could be the Institutional Robotic Board.
Oh, I see. Yeah. I mean, maybe you know, the IRB, I suppose, serves that function for us. You know, when we're bringing not us to work with the robot, they review it and say, you know, this is okay or not. And I have personal guidelines, like I won't put a gun on my robots. You know, I won't make models that do that. I don't want to do that. But I will, you know, I do take DoD funding, and I do think about search and rescue sorts of things. You know, search and rescue, you know, sounds really nice, but then, you know, you can imagine searching and not rescuing, and I know that, and I don't like that, but it's good money, and more than that, it's interesting research problems. And the research, what I tell my students is, like, I don't want to work on something that only has or primarily has bad applications, you know, applications which I think are morally wrong. But I will work on something. I think it's almost impossible not to work on something that has some morally bad applications, as long as there's many not morally bad applications. Because I feel like if you don't, I mean, maybe that's a compromise with sin or something, but like, but like, it's hard to work on anything. Like, it's hard to find anything that has no morally bad applications. Like, you know, anything. You know, like I'm playing with this orange right now. I could throw it at somebody, and it's an orange, right? Like, you know, I could think of something bad to do with it. So.
No, go ahead.
Let me ask a follow-up to that. So I'm let me guess at one. I really liked that you were kind of enraged that they didn't release the whole set, the DeepMind, because it feels like that's one of the just throwing this out there, that one of the anchors is something like sunlight's the best antibiotic, or having a truly open framework for the knowledge generated allows for the corrective to be invented by those people who do have the moral compass, or something like that, right? Like, so is that some part of the value system that goes into it?
Right? I absolutely believe in that. Like, I think that having, you know, and one of the things I say is that, like, you know, it's incumbent on us, you know, as individuals, as technologists, to work on, and I see this primarily as when I'm training my students, like when you go out and you do stuff, I hope that you think about the applications that you're working on and what it's going to be used for. And I hope that you're the one that's standing up and saying, we're not going to do this. This is wrong. And for me, like I see, one of my roles is to sort of, like we were actually in our drone course just discussing that it's important for us to have a unit on ethics and robotics in the course so that these students that we're sending out have thought about this, and that I think is the strongest antidote we have, is to send the students we train out into the world armed with this sort of ability to do moral reasoning, so that the systems they make, are used for good things and not bad things.
Absolutely. I mean, I think that's certainly the responsibility, but that's our role as educators, right? I mean, it's you communicate knowledge, but you also really have to provide the moral framework in which the information is being conveyed. I think in biology, of course, that the field has been, particularly medical biological sciences, has have a number of guidelines and ethics boards and things, and I think fundamentally, of course, they're great. They but perhaps not enough. And I don't know why. There must be a reason, and I can't think of it right now. It's like why that took off, and that's kind of embedded in research in biology and medical biology in particular, and why not in other fields. Like I actually had a really great set of discussions with Fei Li, about the work that they're doing at Stanford to try and embed discussions about ethics at all level, within all of the classes, so that it's just integrated within the research community, broadly, rather than being this thing on it by itself with a set of rules that everyone should follow. Like that, that I really think the integration of that is critical.
Yeah, we in the CS department also have been having that conversation.
Yeah, great. So
I'll say I just experienced one object lesson in free access because Zoom kicked me out in the middle of what you were saying, Stefanie. Although if I could, it does beg a good question, which is, if free information is one of the correctives along with good ethical training, right, trying to impart your values, there is a scale, right, that this all has to exist at in robotics. It feels like such a big challenge to make actual physical things. I'm just overwhelmed by it. I'm used to like taking really small neural systems and saying, oh, I found one more spike, let me publish my next paper, right? And so, how does that scale fit into, so part of it's a freedom of information, like how could I host the petabyte data set that then I can give everyone access to? How do you immortalize the petabyte data set? Feels like a really crucial question for a university to have to handle if we're going to support the kind of work that's going to create those cool data sets.
Yeah, we were, sort of related to that. We've been discussing with Thomas Serre in CLPS getting more involved in the cluster that he's now leading, partly because, we see the need for more compute, but also, data set storage and access. It all goes together, as we scale that stuff up. It's interesting because we're starting to see a sort of difference in access in industry, in industrial compute environments, that they have access to far more compute resources than we do here in the university setting. And that's changing the sort of work that we can do versus what they can do in interesting ways that may not always be good.
Yes, I completely agree. A university has to get access to compute and its ethics right. And those are maybe the two things the university has to be right now, right? Now values includes a lot of other stuff too, but I fear that. I personally, not to be too specific, I fear that a lot too, that access to the scale of cloud computing, if we can't keep up in academia, in addition to the brain drain that'll just go to industry, there's a real problem in terms of open research.
Yeah.
and how
I mean,
it
I
can
think
go
there's models
forward.
for this in other fields, though. Like if you look at astronomy and physics with the Large Hadron Collider, you know, there's a similar, you know, the Hubble Space Telescope and the like. There's similar large pieces of infrastructure that are required to make progress now in certain areas, and they survived it. You know, they're still able to make progress. They have these giant papers, you know, with lots and lots of authors. In some ways, we've been privileged because we're able to make so much progress on our own.
So I'm gonna take a jump, Stefanie, I know I mentioned your the kind of work that you did in the high schools to kind of reach out to high school students, and there's a couple of high school students I know who are listening and putting in questions. And I'm gonna so, you know, I think it would just be really cool if you could just say briefly, you know, if you were starting out as a high school student and you just wanted to have a massive impact in robotics, like what would you do now? Would you just do the same thing that you did in high school and undergrad and grad, or is like there's something you're like, you have to do this, like this is going to be critical?
I mean, robotics, first of all, is a really big field. There's a lot of different ways to be a roboticist. I think a lot about AI and programming and, you know, what goes on in the compute part of the robot. But a lot of people think a lot about the mechanical design of the robot. There's people that focus on sensors and trying to make better cameras, you know, with more pixels that come in faster. So partly, I think, you know, you should think about like what STEM stuff do you feel most drawn to. I really like this book. It's called "What Color Is Your Parachute?" And it says that like one of the things it says is that there's like some stuff about you that's sort of innate and it's really hard to change. An example might be some people are like really social and they like to hang out with other people. Other people are less driven by that and they're more happy by themselves. And there's other stuff, skills that you can learn. You know, you can learn a programming language, you can learn to solder, you can learn to use a CAD tool. And what you want to find, and then the other thing is that there's like the meaning, you know, like what are you, you know, what is the impact that you want to have in the world? What is the thing that you personally are passionate about in the world? The change that you want to make in the world. And then what you're trying to do is find an alignment between the stuff about you that you can't change and the stuff that you're passionate about and skills that you can of course learn, right? So you have to decide what skills to learn so that, you know, you're like the Falcon 9 aimed up at the International Space Station and you can launch yourself like a rocket. And of course that's an exploration process. You know, you don't come in, you know, I often tell my students when they're applying for PhD programs, they're writing this research statement, and it's sort of, they have to tell this story about how the entire trajectory of their whole life was aimed at getting a PhD at Stanford or wherever they're applying to get a PhD. But of course that's a lie. It's never like that. Like, you're exploring, right? You're trying to figure out, you know, what combination of things and what field and what area you're going to be the happiest and the most productive and the most effective. So there's no one answer that I can say for everyone, because everyone's different, and the answer for everyone, you know, what they're going to care about is different. You know, there's a list of STEM things. Programming is really important if you want to do what I do. Linear algebra and geometry and trigonometry and calculus and probability, those are all good things. But really it varies a lot by who you are and what you're interested in doing. And there's really nothing wrong with saying, you know what, like, I don't know if I want to be a roboticist, but man, programming's fun now, so I'm going to go learn to program. Like, that's fine. Nothing's good. Like, that's a great plan, I think. As I said, I'm very opportunistic in my research, and I think that's a, you know, pretty good heuristic. At least if you do that, you're having fun now when you're programming.
Brilliantly said. I mean, I think, yeah, you just captured, you know, that whole do what you love. We're lucky that we can, you know.
Yeah. We're privileged.
We are hugely privileged. I think that that's right. But yeah, I think we've all done that. You just do what you love, and then the rest takes care of itself if you're lucky enough to be able to get on that path. And so, you know, I think it's fun. I love programming, actually. But so back again to where we started, and maybe this may be the last question. There's a few others that are trickling in, but so I did read on your webpage, and I mentioned at the beginning that you said like everyone home is going to have a robot in 20 years, and we probably already have them based on the early definition. You know, of sensing, actuator, and a compute. But like what, okay, I'm going to ask you the impossible question, but what will those robots look like in 2040? What do you think?
Spot Mini. So I don't know if you've seen this out of Boston Dynamics, but they've begun selling them now, these quadrupedal robots. I do think they're going to have legs because I think it's too hard to move in our existing home environments without them. And I think they're going to have manipulators of some kind. So the Spot Mini is a pretty good first draft of that, in my opinion. I was super excited about that particular robot because I see the hardware, you know, that can really move around, can go everywhere I can go. It can walk up and down stairs and stuff. It's not going to get stuck by the thick carpet that something on wheels is going to get stuck on. So, and I think, you know, it may be that we'll move to a humanoid platform. So that is something with arms and legs. So if you've seen the DARPA Robotics Challenge robots, the Atlas robot from Boston Dynamics and other sorts of robots, the Hubo, the humanoid platform is compelling because like the world, we've designed the world for humans. So if we can put a robot in that form factor, sort of by construction, hopefully physically anyway, the robot will be able to open the doors and open the drawers and fit through things that we can fit through and the like. So I do think there's reason to think that, you know, that the robot that penetrates into the home is going to be that kind of a form factor. I think it has to have legs, and I think it's plausible that it will be humanoid. But really, I don't know. I said 40 years in part because that's a really long ways away. So no one's going to check me.
Did you say 40 or did you say 20? I think you said 20.
I might have said 20. I think.
I think you said 20. Maybe you said 40, 20 years ago.
Yeah, maybe.
Good prediction.
Yeah.
Yeah. So those constraints of how we have, you know, built the world around us based on, you know, our ability to maneuver is going to constrain, obviously, the shape and the form and the abilities that you're looking for in a robot that's going to enter the home. Yeah. I guess one more question. So someone mentioned that in the background of your screen, there's some musical instruments.
Yeah.
And they want to know.
Oops.
Is this influencing your research, Stefanie?
Yeah, I play the ukulele.
Yeah. Yes.
Yeah.
Take us out. Actually, before you take us out, I'm going to mention one quick thing, and then this is brilliant. Thank you, whoever asked that question. The ukes in the background, but I'm just going to say, you can join us. Stick with us because Stefanie is going to take us out with the ukulele. But on June the 30th at 3:30 to 4:30, Oriel Feldman Hall in the Clips department is going to discuss how emotional appeals increase social distancing behaviors during COVID-19 pandemic. So over to Stefanie. Thank you. This was brilliant.
Mama Pajama rolled out of bed and she ran to the police station. When Papa found out, he began to shout and he started the investigation. Was against the law. Was against the law. What the mama saw was against the law.
The multi-talented Stefanie Tellex. Thank you. Thanks everyone for joining
Fabulous.
us.